to all and welcome to this lecture. We are in module 10, lecture number 1, DC gate current. In this lecture, we will discuss about DC gate current in MOSFET and oxide breakdown. These are the learning outcomes of this lecture, which will help you to understand the physical origin of DC current in scaled MOSFET by relating the oxide thickness reduction to quantum mechanical tunneling phenomena. In this lecture, we will see the difference between Fowler-Norden tunneling and direct tunneling and when this tunneling will dominate. This will also help you to distinguish the normal gate tunneling behavior from oxide breakdown by examining the abrupt increase in gate current in critical electric fields. So, let us get started with a quick recap. In previous lecture, we have discussed that polysilicon is widely used as gate material in MOSFETs, where the oxide thickness is very small. So, in some sense, to increase the effective oxide thickness, instead of metal, we will use polysilicon gate. But when you replace the metal gate by a polysilicon gate, then there will be a problem, or there will be a inherent physical property as poly depletion comes into picture. Meaning, if you consider a system of two terminal, which is gate and body, and you applied a gate to body voltage, considering the gate is made up of polysilicon, then when you apply a positive voltage, because of that there will be a depletion in the polysilicon. As you apply a positive voltage, per positive Q charge at this side, it causes a negative charge at the surface, or it will attract the electron from this side to this side, correct, and hence this is depleted. Because of the polysilicon depletion, there is a psi poly drop appear into the system. That is what it influences the total potential and charge balance equation of the system. In earlier lectures, when we discussed about two terminal MOS structure with metal as a gate, we said that VGB is equals to psi ox plus psi s plus phi ms is a potential balance equation. However, when you discuss about polysilicon depletion, it means there is a poly drop is there, which is a poly surface potential or poly potential, then psi poly will comes into picture. This change in potential balance equation will also cause the change in charge balance equation, that is the total charge balance equation for this system is Q poly dash plus QB dash plus QI dash plus Q naught dash is equals to 0. Then we have discussed that how this polysilicon gate influences the MOSFET operation when it operates in weak inversion and strong inversion. In weak inversion, when we considered that the inversion charge is almost 0, then we can simply relate the poly charge is approximately equals to minus of QB dash, where we equated this and found that Q poly is nothing but square root of 2 into Q into N poly into psi s into square root of psi poly, and QB dash is minus of minus square root of 2 into Q into Na into epsilon s into square root of psi s. In this sense, we can relate a relation as N poly into psi poly is equals to Na into psi s. This equation later used to find out the effective oxide thickness, when we said that when the polysilicon depletion is coming into picture, the effective oxide thickness is increased as this thickness plus the thickness of the oxide. So, we have also found the change in the effective oxide thickness. Then we said that the slope factor, which is nothing but 1 plus C B dash by CO x dash, it can be given by 1 plus C B dash by C poly ox. This is a new layer which we defined as a combination of the polysilicon depletion as well as the original oxide, and hence we found that the change in the slope is given by the ratio of Na with N poly. Then we also said that this polysilicon depletion significantly influences the operation of MOSFET when it operates in strong inversion, because the VGB voltage or VGS voltage which you are applying through the over the MOSFET gate to operate in a strong inversion will also drop across the polysilicon gate, and hence the threshold voltage will increase. So, the new threshold voltage VT naught cap can be written as VT naught plus psi poly, and if the threshold voltage increases for the same amount of gate voltage, the inversion charge will reduce. That is what the polysilicon depletion creates a significant influence in your MOS operation in weak and strong inversion. Now, let us see the another effect related to the gate oxide itself, that is related to gate oxide itself, which is DC gate current. A key classical advantage of MOSFET over BJT is that there is no DC gate current, meaning if you see the symbol of MOSFET also, we make the symbol like this, mentioning this is a source terminal, this is a drain terminal, and this is a gate terminal. Between the gate terminal and the channel there is a separation which clearly states that there is no DC gate current, that is Ig is equals to 0. And if you remember, we started our analysis of founding of the basic building foundation of MOSFET with the same assumption that Ig is equals to 0. That is what in early days we use this device as insulated gate field effect transistor. This is the good advantage over BJT, because these devices are useful when we operate MOSFETs for low power and high input impedance circuits. But let us see why there is no gate current when we talked about MOSFET. If you make a band diagram of the MOSFET, so let us consider this is your MOSFET where N plus is source, N plus is drain this side, and I am making an oxide a bit to show an overlap area also. So, this is an oxide region and this region is an overlap region. This region is an overlap region at the source side. It means the oxide which will come over the drain and the source in practical MOSFETs. So, now what will happen if I draw the band diagram along the cut line AA dash? It means I am taking metal at this side or gate and this side as silicon or substrate or body. In between we do have oxide. We already discussed about this kind of band diagram when we were discussing about two terminal MOS structure. Then we found that if you do have a metal at this side, there is a Fermi level which is aligned to the Fermi level of the silicon if considering all the voltages are 0. So, let us consider your gate voltage is exactly equal to flat band voltage, VGB is equals to V flat band voltage, and drain voltage is 0. So, if you draw the band diagram along the cut line, you will get that you do have a metal here which is having a Fermi level like this EFM. After metal you have an oxide which is have a band gap of 9.1 electron volt, which is silicon dioxide, and after this you have a silicon. So, band gap is around 1.1 electron volt. Now, there is a difference between this conduction band energy to this conduction band energy of all about 3.1 electron volt. Now, when you apply a positive voltage at the metal, then what will happen? The metal Fermi level will go down by the same amount with which you are applying the voltage, let us say VGB. Because of that, there is bending in the semiconductor bands. That is what we have discussed, how the depletion and inversion takes place. So, when you apply a positive voltage, right, then there is a bending at this side and the electron will come in this triangular potential barrier. Now, the oxide is thick enough, then this electron will be confined. One side there is a thick barrier and the difference of this height is approximately 3.1 electron volt, and one side is the conduction band which is bent in the substrate. So, electron cannot move along this direction, correct, because electron does not have this much energy to climb the barrier and go at this side. But what will happen if you reduce the oxide thickness? If you reduce the oxide thickness significantly in scaled MOSFET, then the electron will be confined here and there is a possibility of quantum tunneling, meaning quantum mechanics says even if the carrier does not have enough energy to surpass the barrier, there is finite possibility that the electron may tunnel through this barrier if the barrier thickness is very small. And hence, if the thickness of the oxide is very, very small, then there is a possibility that there will be a tunneling from the conduction band of the source or substrate to the gate. And if the electron will move from right hand side to left hand side, it will constitute a current from left side to right side, which is called as gate current. Now, if the oxide thickness is not too thin, meaning if the order is greater than 4 or 5 nanometer even, then there is a tunneling happens which is called polar Norden tunneling. This tunneling occurs even in moderately thin oxide layers where high field present, and this tunneling happen exactly at this region where the triangular potential forms. However, when the oxide thickness become very thin in comparison to the previous oxide thickness of 4 to 5 electron volt, 4 to 5 nanometers, if it is of the range of 3 to 2 nanometer, then there will be a band to band tunneling happen. In both the cases, the electron is moving from the substrate to the gate and constitute a gate current. So, that is what a DC gate current is non-zero when the oxide thickness is very small, correct. Now, let us consider if you apply a voltage, then how the gate current flows in the MOSFET and how it constitutes to the overall current. For example, we are applying a positive gate voltage here, and because of that there is inversion happen. So, let us consider at this case the drain voltage is positive but very small. In that condition, if I draw the band diagram like this inversion charge will tunnel to the metal, right, because of this band bending what we have discussed so far. Because if I plot a band diagram like this is gate and you are applying a positive voltage, and here you have an oxide which is thin enough, and this is Fermi level of substrate, this is conduction band, this is valence band, this is Fermi level, intrinsic Fermi level, and here this is Fermi level, let us say for p type substrate. This is the Fermi level for metal. Now, in this case EFM, now in this case if you apply a positive voltage at the gate, this band will go downward by that amount, and the bending will be there in the semiconductor inside the substrate, and hence the carrier will tunnel through this thin oxide, constitute a gate current. Now, where does this gate current go? If the gate current is coming here in the channel, ultimately it is having two parts. One portion of the gate current can go towards the drain and one portion of the gate current go towards the gate. So, we can say this is IGS, gate to source current, and one is gate to drain current. The formulation of this gate current is complex because we need to include the quantum effects or quantum models. However, in simple way we can consider how we can calculate the total gate current density. Here let us consider JGX is the total gate current density. It means the current per unit gate area is actually equal to or directly proportional to what is the amount of inversion charge present in the channel, because these charge only will tunnel. Second, it depends upon the probability, right, through which the tunneling happens. And the third is what is the oxide thickness, what is the oxide electric field along the X, where this side the current is flowing and hence the electric field in the oxide, correct. So, if you remove the proportionality constant, you will get Jx is approximately equal to beta t into minus of qi dash into ptx into eox, which is a function of x. Here the probability function is can also be expressed in terms of electric field, which decides how much probability that the electron will tunnel from this inversion charge layer to the gate and constitute a current. Now, so if we consider the total gate current IGC, we can simply calculate by multiplying the area. So, let us consider delta x become a small differential and differential area, differential length over which we are actually calculating the current. So, if you integrate with 0 to L, it will give you what? IGC, the current between gate to channel, IGC. And as I said, does this gate current have two components? One component will go in the gate in the source side, one component will go at the drain side, and hence we need to have some weighing factor in terms of x, in terms of position, to find out these components. So, in general we can multiply with 1 minus x divided by L dx when we calculate IGC, the component which will go towards the source, and we will multiply with x by L when the component will go towards the drain. These expressions indicate that the current generated close to the source, right, contributes more to IGS, and the current generated close to drain constitute more towards IGD. The total gate current is nothing but IGC is equals to IGS plus IGD. So, this is the formulation we have done when VDS is small, is very small, you can say. But what will happen if you increase the drain voltage? So, let us plot the gate current with respect to increasing drain voltage. As we have argued that in the MOSFET, when the gate current flows, right, this is having two components, one will go at this side and another will go at this side. But the moment you increase VDS, the difference between the gate voltage and the drain voltage reduces, meaning VGD reduces because you are increasing drain voltage. If the difference between the gate voltage reduces and increase in drain voltage also reduces the inversion charge, we have already discussed in previous lectures. That is what the probability of tunneling here near the drain will reduce, and that is what when VDS is equals to 0, the gate and drain current probability is just 50-50 or the contribution is just 50-50, but when you increase VDS, the gate to drain side current is smaller than gate to drain current at source side. Now, what will happen if you increase VDS beyond a certain point? For example, if you are increasing VDS and you attain a saturation point, it means VDS dash. Beyond that point, if even you increase VDS, the channel is pinched off, and if the channel is pinched off, there is significant decrease in VGD, right, but at that the same time the lack of electrons are available, which will tunnel from the surface to gate, and hence it will give rise to a current. That is what IGD goes constant and it becomes a independent function of VDS. That is what we can simply say that IGD is a function of gate voltage as well as drain voltage. Further, we can find out how this voltage flows, how this current flows in terms of large VDS and smaller VDS. To do so, let us plot IDVG with respect to, let us plot IG, the gate current, with respect to VGS. Okay. Now, what we are doing, we are considering there is an overlap region also, which is in practical it is present. So, this is gate, this is an oxide, and there is an overlap region which is circled green. Now, if you apply a positive voltage, then what will happen? The bending will look like this. and the electron will tunnel from semiconductor to gate, which gives rise to a current in this direction and give you a positive Ig. However, what if you apply a negative voltage? If you apply a negative voltage, the bending will look like this, and there is finite chance that the electron will tunnel from gate to semiconductor. It means it will give rise to a negative current, which is Ig. So, let us see what will happen if you increase Vg from 0 and sweep in both direction, either in both direction, meaning in positive and in negative direction. So, let us consider for a VDS 0 volt case. If VDS is 0, you are increasing Vg, meaning this bending will be like this, and hence the electron will tunnel in this direction. So, there will be a gate current. So, the gate current increases with VGS. So, this green region is a first case. The second case, let us sweep the gate voltage to a negative value. If you sweep the gate voltage to a negative value, then this is the case. The bending will be at other side, and hence the electron will tunnel from this side to that side. It will give rise to a negative current, right. Though we are plotting this current in a log scale, so we are just taking a magnitude, right. So, this will give you a negative current. So, this is a case number 2. Now, in the case number 3, let us consider we are increasing VDS to higher value, let us say VDS as 1 volts. Now, consider the point when Vg is equals to 0, but Vd is 1 volt. So, I am redrawing a band diagram of this structure, saying that if Vg is equals to 0 and Vds is equals to 1, meaning what? The band diagram look like this, or the MOSFET structure in the overlap structure is look like this. This voltage, which is a drain voltage, is positive, and the gate voltage here is 0. If you see carefully, the bending will look like this, right, in the overlap region. So, in the overlap region, the electron will tunnel from the oxide to gate, and hence it will give rise to a negative current. So, that was visible that if VDS is 1, but VGS is equals to 0, you have a negative current. This slope is coming like this, right. So, this is case number 3. When VDS is equals to 0, your ID or Ig is negative, correct, because of this reason, because of the tunneling, reverse tunneling from drain to gate due to this overlap section. Next, when the fourth case you increase VGS towards the positive side, then what will happen? This band will again, first it will align like this and it will bend like this. So, when it will align, there will be a 0 gate current, meaning the bending was like this. When you increase VGS, the bending will be aligned and there is no tunneling, and hence because of that you will get a notch here, which is at some higher positive gate voltage, correct. At that time the gate voltage is 0. As I mentioned, this side is positive gate current and this side is negative gate current, and this scale is log. That is what you are getting a notch, which shows that at that moment the current is 0. And now the fourth case, if you apply more negative VGS, the tunneling and current or the gate current will be more negative, like this. So, this is the fourth case, okay. So, it is clearly visible that how my gate current increases or decreases or varying in the MOSFET in terms of VGS and VDS. In addition to the terminal voltages, the gate current is completely depend on the oxide thickness. If you reduce the oxide thickness, then the gate current significantly increases. In layman words, if you reduce the oxide thickness by 0.5 nanometer, then the gate current will significantly increase or become 2 times, right. So, the dramatic increase in the gate current with reduced TOX makes further scaling of conventional SiO2 gate oxides impractical. That is what you need to think about new geometry scaling like effective oxide thickness or polysilicon depletion. There is an oxide breakdown. What it means is, as we have discussed, that when the geometry of the oxide is scaled, then there is a possible gate current which flows through it, right. So, Ig is not 0. But if you increase the voltages, like we have seen, if you increase VDS or VGS, the significance of the gate current increases, and there is a possibility that this gate current causes a permanent damage in the oxide. So this is called oxide breakdown. This decides the aging of the devices. Typically, oxide breakdown occur at around 1 volt per nanometer. For example, if the oxide thickness in MOSFET is 2 nanometer, then it can hold or withhold till 2 volts of supply. Generally, for reliability purposes, MOS devices are typically operate 50% less than of that voltage, meaning in 2 volt, 2 nanometer oxide thickness MOSFET will keep a power supply is around 1 volt only. So let me summarize this lecture. In this lecture, we have discussed about DC gate current. We said that though we said in ideal MOSFET there is no gate current, and this is a good advantage we preferred over BJT, whereas in scaled MOSFET there is a significant amount of gate current, which is IGC. In general, in MOSFET this gate current does have two components, because when the gate current flows in, it is having two components, one is IGC and one is IDGD. This gate current is dependent on the probability function, which is IGC is directly proportional to the electric field in x direction, the probability in x direction, and the inversion charge present in the channel. So if you increase the voltage, let us say VDS, the inversion charge density near the drain side will decrease, and hence the contribution of IGT will reduce in overall IGC. So we will stop here for today. Until then, take care.